In the ceaseless pursuit of innovation, humans continually redefine what it means to be alive. From the dawning of the artificial intelligence era to the advent of genetic manipulation, we've journeyed far into the realm of what once seemed impossible. Today, we stand on the brink of yet another monumental shift, encapsulated in the emergence of a novel entity known as the Xenobot. These minuscule synthetic organisms, no larger than a speck of dust, are the progeny of a compelling marriage between the organic and the artificial. Crafted from the stem cells of the Xenopus laevis frog, they aren't a traditional species of animal nor a typical robot. They represent a brand new class of artifact, a programmable, living organism. As we delve deeper into their world, we find ourselves in the midst of a thought-provoking discourse on life and the boundaries of technology. Xenobots are an extraordinary culmination of scientific endeavor. Their bodies are assembled from 500 to 1,000 living cells, resulting in simple shapes, some even sprouting squat legs. Despite their size, mere millimeters in length, they boast an impressive repertoire of abilities. They can move, work together, heal themselves, and in an almost Pac-Man-like fashion, assemble new Xenobots from other frog stem cells in their environment. This ability to self-replicate, an idea once mulled over by mathematician John Von Neumann and later visualized in the nanotechnological concept of gray goo by Eric Drexler, brings us to a new frontier of discovery. However, this frontier is not without its inherent risks. From the creation of the artificial polio virus, which despite its synthetic origins, managed to self-replicate and infect mice, we know that the line between technological marvel and potential menace is precariously thin. The potential applications of Xenobots are as myriad as they are thrilling. From cleaning up pollution to delivering drugs to tumors, and even repairing damaged tissue, these programmable life forms could revolutionize various sectors. Imagine a future where the lines between biology and technology blur, where living robots become commonplace, and diseases are combated by entities of our own design. Yet, this brave new world does not come without its ethical quandaries. As we venture into this uncharted territory, we must grapple with questions that transcend the limits of science. Should these Xenobots be classified as truly alive? If so, what rights do they possess? How do we ensure their responsible use and ward against potential misuse in warfare or the creation of designer life? The United Nations Biological Weapons Convention and the 1925 Geneva Protocol and Chemical Weapons Convention provide some legal guidance, but much remains open to interpretation and discussion. The advent of Xenobots reflects a testament to human ingenuity and our relentless pursuit of knowledge. Yet, it also underscores the need for thoughtful, robust conversations about the implications of our creations. In the world of science, every answer uncovers new questions, each breakthrough paves the way for new challenges. As we contemplate the future of Xenobots, we must also reflect on the lessons learned from our past experiences with emerging technologies. The development of Xenobots is akin to the nascent stages of nanobots, entities created from non-living materials. While these two differ in their material origins and creation processes, they share the potential to alter our understanding of life and technology. How are Xenobots different from nanobots, you might wonder? The contrast lies in their origin and assembly. Xenobots are born out of living cells, a product of directed evolution where scientists employ computer programs to shape new life forms. They are crafted using 3D bioprinting technology, assembling cells to form the plant organism. These tiny beings, only a few millimeters in size, are made of living tissue and are far larger than their nanobot counterparts. Nanobots, on the other hand, are non-living entities. They are the result of top-down manufacturing, a process where machines are used to construct these minute devices from non-living materials. Although the concept of nanobots predates Xenobots by a few decades, they are still in their infancy in terms of development. They hold promise in several areas, such as medical diagnostics and drug delivery, but their potential remains largely unexplored. Xenobots, despite their nascent status, have demonstrated a wide array of potential applications. They can be programmed to perform specific tasks, including cleaning up microplastics in the ocean or delivering drugs to cancer cells within a human body. One day, They might even repair damaged tissue or organs, offering a new approach to healing that combines biology, technology, and robotics. They are a testament to the potential that lies at the intersection of these disciplines. Yet, with any groundbreaking innovation come associated risks and ethical concerns. The creation of Xenobots stirs unease about the potential misuse of this technology, either for the creation of designer life or for military purposes. The thought of these entities being used to extend human lifespans indefinitely stirs both intrigue and apprehension. These concerns underscore the necessity for a responsible and well-regulated approach to this emerging field. In 1966, mathematician John Von Neumann introduced the concept of self-reproducing automata, a concept that resonates with the nature of Xenobots. In the realm of nanotechnology, Eric Drexler painted a bleak picture of a world overrun by self-replicating nanobots, termed gray goo, that consume everything in their path to propagate themselves. The creation of a synthetic polio virus in 2002, crafted from custom DNA sequences, highlighted the dual nature of this technology. It is both an incredible scientific achievement and a potential danger. This synthetic virus demonstrated the ability to self-replicate and infect mice, further reinforcing the necessity for a thorough understanding of the implications of creating self-replicating organisms. The latest iteration of Xenobots has taken a significant leap by exhibiting the ability to replicate in a way previously unseen. Rather than reproducing in the traditional biological sense, these beings assemble new Xenobots from frog stem cells in their environment, a process that oddly resembles the gameplay of Pac-Man. This peculiar form of replication draws us one step closer to creating organisms that can self-replicate indefinitely, a concept that is as exhilarating as it is daunting. As we stand on the precipice of this new era of biological innovation, it's important to remember that every technological advance is a double-edged sword. The creation of Xenobots offers a glimpse into a future where biology and technology intertwine in ways we never thought possible, yet it also raises critical questions about the responsible use of such technologies. It is our moral imperative to ensure that our ceaseless quest for knowledge does not outweigh the ethical considerations that this new frontier presents. The future of Xenobots, and the future of our world, will depend on it.